Okay, so yesterday we learned about a lot of characteristics of polynomial functions. So we went higher than degree 2. We spent 2 units on quadratics. Then yesterday we started looking at the characteristics of degree 3, 4, etc. And we're going to continue with that today, looking at transformations of polynomial functions. Kind of relates back to what we did with quadratics. So the first one here is a basic y equals x cubed. You know how to do it for y equals x squared? Very similar here. So it was okay, we're going to describe the transformations starting with stretches. So that's a vertical stretch by a factor of 1/2. Then reflections next. So reflection in the x-axis. Remember, that's changing the sign of y. So that's in the x-axis. And then it doesn't matter which translation you put first. Vertical translation up 3. Horizontal translation left 4, right? Opposite of what you would normally think. So the point -4, -64 lies on the original graph. Determine its corresponding image point on the transformed. So start with that point. Now we're going to do a vertical stretch. So by a factor of 1/2, so I'm going to multiply by 1/2. Then I'm going to do a reflection in the x-axis, so multiply by -1. Now, it doesn't say, well, it does say determine, so we should show steps here. And then translations, because they're with separate coordinates, you can do them all at once. So we're going to go left 4, so that would be -8, and up 3, that would be 35. Okay, so this subtract 4, this, subtract 4 and up 3. Okay. Now, the general mapping then for point xy, well, what's happening to the x's? The only thing we did here was go left 4, so that's going to be x minus 4. For y, we did the stretch and reflection, so that would be -1/2 y, and then we went up 3. Okay. So if you put in your original x value into here, you should get -8, which you do. If you put -64 in for y here, you should get 35, which you do. Okay. So that was a cubic. It was kind of in what we would call, not a vertex form, but it's really where the point of inflection is. It's not simplified or factored. The next one is a cubic, but it is factored. So remember, y-intercept is when x is 0. So you can put 0 in here. You can just eyeball it. So 0, 0, 0. So that's going to be 2 times 1 times -4. So that's -8. If it was in simplified form, remember the y-intercept is the constant term. X-intercepts, because it's factored, think back to quadratics. It's going to be the opposite side of the constant. So -2, -1, and 4. Okay, from each factor. So if we vertically stretch this p of x by a factor of 2 about the x-axis, the y-intercept, well, think about it. If you've got your y-intercept at -8 here, and you're vertically stretching by 2, it's now going to be at -16. X-intercepts, so there's 1 there and 2 there. The y value is 0. So if we stretch that by 2, they don't change. So they stay as -2, -1, and 4. The vertical stretch about the x-axis did not affect the x-intercepts because they are invariant points. So remember, x-intercepts our varied points, they don't move on a vertical stretch or on a reflection. Write the equation of the transform function in terms of x with y isolated. So, here we can replace in front of the factors our vertical stretch by a factor of 2. So in Math 30 next year, we'll go through this in much more detail with transformations. But think back to quadratics. If you're stretching by a factor of 2, you're multiplying your original function by 2. Okay? Vertical stretch. We're not going to do, we'll do horizontal stretches as well, but that's going to affect the axis. Okay, so, and remember, we already said the x-intercepts won't change. So that's the equation of the transform function of x with y isolated. We're just going to leave it in factored form. And then let's, in part D, determine the y-intercept and check it. So y-intercept is when x is 0. So really you're finding p of 0. So that's going to be 2, 1, -4, which is -60. And that's what we figured it was going to be. Okay, if p of x is reflected on the x-axis, so we're not stretching as well. So we're just doing a reflection. So the y-intercept, it was near -8. If we reflect that in the x-axis, it's now going to be +8. And again, x-intercepts won't change. So there's still -2, -1, 4. The vertical stretch about the x-axis did not affect the x-intercepts because they are invariant points. So they don't vary, right? They stay the same. Write the equation of the transform function in terms of x. So same as last time. Actually, I called that p of x before. I should have probably called this, let's call it f of x there. A new function, right? I'll call this g of x. And so I'm going to change the sign of your original function. Okay, and then find the y-intercept. Which is +8, which is what we thought we did. It was good enough, right? So the algebra confirmed it. So a vertical stretch or reflection on a polynomial function does not affect its x-intercepts as they are invariant points. The x-intercepts of y equals x minus b, x plus c, x plus d are the same as the x-intercepts where you multiply it by an a value. It could be positive or negative. It is easiest to determine the x-intercepts of a polynomial function. For what form is this in? It's in factored form. Okay. It's a big part of what we're going to do in this unit. Okay, so previously we looked at functions whose x-intercepts were all different. The more factors the polynomial had, the more x-intercepts it had, as shown below. So here was a quadratic. There it is in factored form. The x-intercepts, you can see it, we've plotted it. So 0 and -3, but you can also see it from the factored form. And that's a degree 2. Okay, then the next 3 factors. X-intercepts are 0, -3, -1. You can see them 0, -1, -3, and degree 3. Next one has 4 factors. X-intercepts are 0, -3, -1, +1. And you can see them all on your graph. And that's degree 4. And another one, 1, 2, 3, 4, 5 x-intercepts. These happen to be all different. So when you see them graphed, the graph goes through all of the x-intercepts, obviously, and keeps continuously going through those. Okay, we'll talk about behavior here at each x-intercept in the set. The degree here is 5. Okay. So what is the behavior of the graph at each x-intercept? It goes straight through. Okay, so straight through from below the x-axis to above, or above the x-axis to below. This is because each of the factors in the equation has an exponent or multiplicity of 1. What happens if one of the factors in the equation has an exponent greater than 1? So this is what we call multiplicities of zeros. So basically, a multiplicity is how many factors there are of that equal factors, I guess I should say. So you look at the exponent on each factor. So the graphs of several polynomial functions of this form are shown, and n is increasing each time. So we're keeping x plus 1 as a factor, okay? So it goes just through there and just through it too, because the exponent on x minus 2 is 1. Now we're going to square it. So we've got this. Take a look. Just goes through at -1. Now it just touches at 2. Kind of looks like part of a parabola, right? X1 goes through at -1, and then it zigzags through at 2. Okay, we call that a point of inflection. Okay, where a graph is going increasing all the way through, but levels off to be basically horizontal, and then keeps going. Okay, I call it, the non-math word is zigzag, right? But it's changing from opening down to opening up. That's a point of inflection, and you'll talk lots more about that in calculus as well. Okay, so that was for degree 3. Then degree 4 goes through at -1, and then again, just touches at 2. It's kind of flatter there, right? It's wider. Still kind of looks a little bit like a parabola, right? But it just touches. Sometimes we call that, that point there, or the x-axis, is a tangent point to your graph. Okay, so that's for degree 4. And we'll keep going. Degree 5, again, has a point of inflection, wider, levels off earlier for that. Then degree 6, again, kind of a U shape, but really wide, has a tangent point. Degree 7, point of inflection again, even wider. Okay, if you take a look at the scale on these, you can really see the difference. And then here, again, degree 8 is that kind of U shape with the tangent. So that there's some patterns here. Okay, so that's our next question here. If n is even, it says describe the behavior of the graph at the x-intercept of 2 if the exponent n is even. Okay, the graph just touches the x-axis at x equals 2. It does not pass through. So, i.e., the graph is tangent, or actually, I should say it the other way around. So, the x-axis is tangent to the graph of x equals 2. Okay? And then if it's odd, but not 1. Okay, so the graph passes through the x-axis at x equals 2. Okay, so here is a little slow here. It has a point of inflection. And so you can say where, i.e., it goes from opening down to opening up. Okay. So it's important to say point of inflection and going from opening down to opening up because when the exponent is 1, the very first graph, it doesn't have that. So 1 is an odd number, 3, 5, 7, 9, etc. are odd numbers, but the difference between multiplicity of 1 and any other odd number is that it passes through but doesn't have a point of inflection. So the graph passes through there. Okay, but does not have a point of inflection. So you can say it passes through in a straight line, but it's not actually a line, so you have to be a little bit careful about that. So, but does not have a point of inflection. Okay, and then describe the behavior of the graph at the x-intercept of -1 for all of these functions and give an explanation why. Well, same thing. It's just like when the exponent is 1, right? So the graph passes through the x-axis. X equals -1. Get my computer to speed up here. There. Not have a point of inflection. Very slow. Okay, so that's the biggest thing here. We want to look at the degree of the factor. That will tell you the shape of the graph at that particular x-intercept. So if it's an even exponent, it's going to just touch it. If it's an odd greater than 1, then it's going to have a point of inflection, so pass through, but not straight. It's going to have a point of inflection. And if it's equal to 1, it's going to pass through, not have a point of inflection, but be almost like a straight line. Okay? It's not actually a straight line, but it's the closest to straight you can get. Okay. Okay, so I've actually filled in this already, but the example here says we would say the function x plus 1 times x minus 2 to the 4th has degree 5 because there's 4 x's multiplied together there and 1 x there. Exponent on this bracket is 1, understood to be 1, so it has a multiplicity of 1 at -1. This has a multiplicity of 4 at x equals 2. Okay, so that's going to help us graph a bunch of these polynomial functions. So let's look at some examples. For the following polynomial functions, fill in any blanks and do a rough sketch of the function without a graphing calculator. Verify your rough sketch with a graphing calculator. Okay, so first one, it's all in factored form. Got a leading coefficient of 1/12 and all the factors there. So the degree, we want to look at how many factors have x in them and count out the degree. So there's degree 3 there, degree 2 here, and degree 1. So that's going to be degree 6. Sign of the leading coefficient. So you need to be careful. It's not necessarily the A value. You just need to check, make sure all of these are positive, which they are, so then it is positive. And behavior, so the graph extends, does it go up or down, in which quadrants? So this is a little bit back to yesterday and a little bit from today. So this is degree 6, so it's an even degree. So that means it's either going to be both opening up or opening down with zigzags in between. If it's a positive leading coefficient, remember it's always going to go up in quadrant 1. So I like to go there, start and end in quadrant 1, so up. And because it's an even degree, it's also going to be up in a horizontal quadrant, which is quadrant 2. Okay. The y-intercept is when x is 0. So just do a little bit of work here. That's -1, 3 squared, -4 cubed. And what's that going to be? It's going to be negative times a negative is a positive. And then 64 times 9 over 12. So 4 goes into that 16, and 3 goes into that 3, so 48. Okay. So to be specific about the multiplicities here, so first factor, that gives us a 0 1/2. Multiplicity is 1, which is odd. It's going to go straight through, right? Next one is -3. Multiplicity is 2, which is even, so it's going to be U-shaped. Up or down, we'll have to figure that out. X equals 4. Multiplicity is 3, which is odd, and that's going to have that zigzag. So use all of the above information to sketch the graph. Okay, so we do know a y-intercept is 48. We know it's going up here, so I always just do 2 arrows to help me get started. Then I'm going to eyeball the x-intercept, so 1/2, -3, and +4. Okay, and so with the +4, it has a multiplicity of 3. It's got to end up in the first quadrant going up. So I'm actually going to start it here and do that zigzag down. And I'm going to have to come back up to the 1/2. And the 1/2 just goes straight through. And then go up to my y-intercept. I'm going to come back down to -3. Oops, moved it. Okay, and so that is, there we go. That's a tangent at -3, so a U shape. Almost make my original arrow there. Oops, and then I'll erase those ones. And the arrows on the end. Okay, and then the y-intercept here is 48. Oh, here. Do that. Okay, so that's a rough sketch. So the domain, all polynomial functions have domain of all real numbers. The range here, we are going to have to use our graphing calculator. That's why it says 2 here. So let's see, got to get mine out here. Okay, so I've entered my polynomial function into y1. You can start with a standard screen because you know the x-intercepts will fall in that standard screen. Now you know your y-intercept is 48. So it's going to be, especially since we're asked to find the range, we're going to need to find the the minimum as well. So I'm going to change my window. I don't need to go quite as wide, so I'm going to go -5 to +5. But then I'm going to go, let's go -50 to +50 to start. That way at least, oops, I didn't change my scale, but that's okay. At least I might see the y-intercept. And it looks like my minimum point is just a little bit before -50. So I'm going to go here. How about I go -70 to +70, so I can see more vertically, and I'll go by 10. That way I don't get all the squiggly lines. Okay, if you want to see all of it, like that, that maximum value in there, you can change your window, but we don't need to. You just need to find that minimum point. So second trace minimum, and you want to cursor close to where you think it is. Enter. Cursor to the other side. Enter. Enter. Okay, and so we want the y value there. Nearest 100, so -53.79. And y is the real number. Okay. Now, going back to the last unit, in a way, except with a polynomial, intervals where f of x is greater than 0. So where is it greater than 0? So no equal signs there. So you can look at your graphing calculator or your sketch. Where is it greater than 0? So it's everything above the x-axis. So you can use a bunch of inequalities. You could actually show here, I'll do it here in red. So above the x-axis, so here, all of this, all of that, all of that. Okay, so x is going to be less than -3, or between -3 and 1/2, or x greater than 4. Okay. You can use the word or, you can use commas. We'll just put that in squiggly brackets. I guess I should probably put x on reals. Okay. And then below is just that blue that's remaining, right? So that's everything else. So that would be between 1/2 and 4. All right. Okay. So next one, you're not sort of given the prompts, you just have to sketch it. So in this case, let's look for our x-intercepts. So we need to remember there's a factor of x there, x minus 2, x plus 2. So there's an x-intercept at 0, there's an x-intercept at 2, and at -2. Okay. Multiplicities. So this is going to go straight through. Okay. Then multiplicity at 2, the multiplicity is 2, so it's going to be U-shaped. So it's going to go up, down, straight through, U-shaped again, and there's your polynomial function. Okay. Intervals where it's greater than 0. So open circle doesn't include anything on the x-axis, right? So that's going to be x less than -2, between -2 and 0. Now you could also say x less than 0 where x is not equal to -2. That's fine as well. Okay. Then I'll use green for less than 0, so that would be all of this, not including this, right? And those, so that would be between 0 and 2 and x greater than 2. Or, as I said, x greater than 0, where x cannot equal positive 2. Okay. So now we're going to look at determining the equations of polynomial functions. We learned degree 1 in Math 10, degree 2 earlier this semester, and so we're just going to review that. So determine the equation of the parabola there in vertex form. So we know a vertex is 1, negative 2. You can even look at it to find your stretch factor or use another point. Or because you are asked to show it in vertex form, we're not going to use our x-intercepts right now. But let's set it up. Y equals a, x minus 1 squared minus 2. I'll use 0.30. So a equals 1/2. And then always rewrite the equation. So that's in vertex form. In simplified form, I'll simplify it out. So that will be x squared minus 2x plus 1. And that would be minus 3 over 2. Okay. All right, so determine the equation of the same parabola, not parabolas, same parabola in factored form and then in simplified form. Okay, so you can take a look. Your x-intercepts there are negative 1 and 3, so some a value, x plus 1, x minus 3, and then do the same thing, substitute a point in. Now, we're going to not substitute an x-intercept in because that's not going to help us find a. We're going to substitute the vertex in, a different point. Uh, 2 times negative 2 is negative 4, so a equals 1/2. Now, if we expand that out, minus, not negative. Okay, do you get the same simplified form? You sure do. Okay. Okay, so when we're looking at degree 3 or higher polynomial functions, we're going to use factored form along with the multiplicities. So here's an example. Graph of a polynomial function is shown at the right. So let's go through x-intercepts. 2 of them, negative 3 and positive 1. Okay, so what are the factors that give those? X plus 3, x minus 1. So what happens at negative 3 here? What's the behavior? So it indicates a factor of, because it's U-shaped like that, an even exponent on the factor of x plus 3. And that zigzag indicates an odd exponent, odd, not 1, exponent on the factor of x minus 1. Okay? So we can finish it off putting in exponents. This is important. We're most times going to ask you to use the smallest possible natural numbers for your exponents. So when we say it's an even degree, we're not going to choose 8, we'll choose 2, unless we're told some specifics about what degree it should be. So x plus 3 is even degree, so that's going to be 2. X minus 1, odd and not 1, so that's going to be 3. Okay, now a value, well, we need to know another point, and so we can substitute that in. All right, so here we'll use that y-intercept, 0, negative 3. So negative 3 in for y, 0 in for x. Okay, so that's a equals negative 3 over negative 9. Oh, what did I just do? Yeah, that's 9 times negative 1 there, which is 1/3. Okay, so now rewrite your equation. Okay. Degree of this is 5, right? Squared and cubed. Oops, that didn't work. And the leading coefficient is 1/3, which is positive, right? Okay, does the end behavior match the degree and sign of the leading coefficient of your equation? So take a look, it's going up and to the right. We had a positive leading coefficient, makes sense. It's an odd degree, so it should then go, as they call it, disco moves in the diagonal quadrant, so it sure does. Next one, algebraically determine the factored form. And it gives you the zeros because it's a little bit, well, no, actually, this one's the hard one, maybe you're not sure about, but it gives it to us, and state the degree. So, factored form. So we're going to have our A. This will end up being 2x plus 3. So we never use fractions. We want natural number, integers as our coefficients and our terms and our factors. X equals 0, so I'm going to actually just fit in the x at the beginning. Kind of better to have the factors that don't have brackets at the beginning. So then I'll put the 2x plus 3 factor, and then the x minus 1. Okay, so we need to get the exponents on these. It says multiplicities to be the lowest possible. Okay, so this at negative 3 over 2 is going straight through. So I'm going to keep that as is. This at 0 is zigzagging through, point of inflection, so I'll put a 3. And at 1, it's U-shaped, so I'll put a 2. Okay. Then we look for another point. So here's a point, negative 1, 8. So I will put those values in. And figure out what A is. So that's negative 1. Negative 2 plus 3 is 1. Negative 2 squared is 4. So A is negative 2. So now I can put that back in and restate my equation. Degree, so there's 3, 4, 5, 6. Okay, the ends are both going down, so you know it has to be an even degree. Okay, negative leading coefficient, so you know it needs to be going down. Okay, the next one, algebraically determine the factored form of the equation of a cubic polynomial function that touches, so is tangent to the x-axis of 3, crosses the x-axis of negative 1, and has the y-intercept of 36. So it's cubic, so you know that already. So y equals a, we don't know that. Factors, so x minus 3, 2x plus 1. Okay, obviously if we left it like that, that's degree 2, so that doesn't make sense. So it says it's just tangent to the x-axis at 3. That means it's got to have an even degree. Okay, so that'll be degree 2. And then a y-intercept of 36, so 0, 36. Going up again here. Okay. So that's a times 9 times 1. So a will equal 4. Okay, and then replace that. Okay, and now you can get started on the practice.